This is part 4 of our final exam review for the semester. In this video, I'll be covering the material since our third midterm exam. So that includes the chapter on friction and the chapters on centroids and moment of inertia. So let's start with friction. Basic idea is we're only going to be dealing with static friction, and the governing friction equation says that when motion impends, the force of static friction is equal to the coefficient of static friction times the normal force. This is only when motion impends. So any other time, we're just going to treat friction as a complete unknown and use our equilibrium equations to solve for it. I'll give you a quick example. If I have a box sitting on a horizontal surface and someone is applying a very small force to it, maybe a 1 pound force, and this is a 10-pound box, and let's put a coefficient of friction of 0.4. Question is, how big will the friction be? Well, let's draw a free body diagram. And on that free body diagram, we'll have our applied force of 1 pound. We'll have a downward weight of 10 pounds. And then at our surface, we'll have both a normal force perpendicular to the surface and a friction force. Friction always opposes motion. So since my 1 pound force would tend to push the box to the right, friction needs to act to the left. Now, I don't know if motion impends or not. So first, let's use our equilibrium equations. Some forces in the x direction, that would say 1 pound minus the force of friction equals 0. So the force of friction is probably 1 pound. And then if I sum forces in the y direction, I can see that I'll have the normal force minus 10 pounds equals 0. So the normal force is 10 pounds. And finally, as a check, I would want to see what is the max amount of friction that surface can provide given the normal force and the coefficient of friction. That's equal to 0.4 times the normal force, or 0.4 times 10 pounds. Turns out my max friction is 4 pounds, which is greater than the friction needed. So the actual friction is what I found from my equilibrium equations. So there's only 1 pound of friction on that box. There is not 4 pounds of friction. So first common mistake I see students make is jumping to use the friction equation when they have no idea if motion is impending or not. So I typically treat the normal and the friction force as two separate unknowns unless I'm told that we're trying to find the condition where motion is about to happen. Then I solve using my classic equilibrium equations for the friction and the normal force. Finally, double check that I have not exceeded the max friction. If I have exceeded the max friction, then this box would have started moving, started accelerating, and it's no longer a statics problem. Second common mistake that I see with friction problems is students assuming that the normal force is equal to the weight. This example I just gave you, the normal force is equal to the weight, but the normal force will not be equal to the weight if I make just a very subtle change to this problem and direct that 1 pound force instead of straight to the side, if I direct it up, or if I direct it with a downward component. Either of those situations are going to change the total forces in the y direction, which means the normal force will no longer equal the weight. This next example I'm going to look at is another condition where the normal force will not equal the weight, because in this case, normal forces will be perpendicular to the surface, whereas weights will be acting downwards. So the second problem is a situation where you would be given the weights, the weight of block A and the weight of block B, and asked to solve for the force P. But the two blocks are also connected by a link, and you might recognize this link as a two-force member because it is pinned on each end, but has nothing else acting in the middle of it. We're told to neglect the weight of the link. So let's see what the free body diagrams would look like. I'm going to draw a free body diagram of each block. Free body diagram of block A. It's on a 45-degree angle, so we can draw it looking like a 45-degree angle. And what forces will act on block A? It will have its downward weight, the weight of A. It will have the link probably pushing to the left on it. I'm guessing this link is going to be in compression and it will push to the left. So we'll call this the force in the link. And then at the surface, I'm going to have a normal force on block A, and then a friction force. If I'm pushing down on block B, and then there's a rigid link here, Can you see that block A is going to start moving uphill? So that means the friction on block A is going to actually act downhill to prevent that uphill motion. Next, let's do a free body diagram of block B, and it's on a 30-degree angle, so I like to exaggerate that a little bit. I don't want to make it look like a 45 because then it can be difficult to figure out whether to use sine or cosine. We've got a force P downhill that's parallel to the surface. We've got a downward weight of B, and then that link force, if the link is in compression, it's going to push outward on both blocks. This is just like in all of our frame and machine problems. I need these two guys to be equal and opposite forces. And then at the surface, I will have, again, a normal force. Call this normal force at B. And then since force P tends to want to push this downhill, my friction force on B would need to be uphill. For this problem, we aren't given any dimensions. So that's an indication that this is not a problem where you need to check if something's going to tip. You're probably not going to make much progress summing moments either because you need distances to sum moments. So I'm going to need to sum forces. And we're asked to find P when motion impends. Can you see that it will only be able to slide at B if it also slides at A? That means that the force of friction at A is equal to the coefficient at A times the normal at A, and the force of friction at B is equal to the coefficient at B times the normal force at B. So we have two equations from friction knowing that motion is about to impend. For block A, you can either sum forces in the normal old X and Y direction if you want, or you can sum them in a direction parallel to and perpendicular to the surface. I think for this one, let's sum forces parallel to the surface, because that'll make it so that my normal force is in one equation and my friction force is in the other, rather than both of them being in both equations. So let's define an X prime direction here and a Y prime direction there. And if I am summing forces in the X prime direction, I will have the friction force at A in a positive direction, and then I will have plus the weight of A times either sine or cosine of 45 degrees. Since it's 45 degrees, it doesn't really matter which one you use. So I'm just going to use sine of 45. And then the link force, so the weight contributes in the positive X direction. The link force, its two components, will be contributing, it'll be in the negative X prime direction. So I'll have minus F link times, we'll use cosine 45 equals 0. And then if I sum forces in the Y prime direction, those also must equal 0. In the Y prime direction, I'll have the normal force at A minus WA cosine 45 minus F link times sine of 45. You can switch those sines and cosines all you want. I simply like to remind myself that when I'm summing in the X prime versus the Y prime, if I had a sine here, I should have a cosine there. And since this force and this force are perpendicular to each other, WA and F link, if this is sine 45, this should be cosine 45. So finally, this one, I think again, parallel and perpendicular makes sense because P is parallel to the surface. And so then P will only show up in one equation, and P is our grand unknown that we're trying to solve for. So why don't we do the same idea? Define a new, call it X double prime, and call this one Y double prime. And I'm going to sum forces in the X double prime direction equals 0. So doing so, I'll have the force at friction at B minus P. And then I'm going to end up with a minus WB times sine or cosine of 30 and plus F link times sine or cosine of 30 equals 0. Let's figure out which one's going to be sine and which one's going to be cosine. This is where I really like drawing my angle kind of exaggerated. My angle here is, there's my 30-degree angle. So when I look at WB, it's much closer to the Y double prime axis than the X double prime, and that means that this is my 30-degree angle. And if I look at my force of my link, there's my 30-degree angle again. For my weight, if I want the X double prime part, that's going to be opposite the 30-degree angle, and opposite will be sine of 30. And then my link For the x direction, x double prime direction, my link is this will be the adjacent direction to the 30-degree angle. So I'm going to end up using cosine of 30 degrees. And let some forces in the y double prime direction. We have the normal force at B is upward. P doesn't act in this direction at all. And we'll have a minus weight of B times cosine of 30 this time, because we used sine of 30 last time. So we'll use cosine this time. And then the only other force that will contribute to the y double prime direction is the link force. And looking at the direction of the link force, it looks like it's got a horizontal force in the positive double x prime that we already used, and it's actually got a downward component for the y double prime. So we'll have minus force of the link times, this time we'll use sine of 30 for the link, equals 0. And this looks like a little bit of a mess, but I do have 6 equations now. I've got 1, 2, here's number 3, 4, 5, and 6. And each equation only has a couple of unknowns in it, so it shouldn't be too difficult to solve for. What I'll do is I'll use these friction equations to eliminate friction, force of friction in equation 3 and equation 5. Those are the only 2 places where friction appears. So that would get me down to 4 equations with 4 unknowns. And we have some equations with normal force and force in the link. This will then have normal force at A and force in the link. So I can solve those 2 equations simultaneously for the link force and the normal force at A. Then I can back up here and get the friction force at A. Then over here for block B, once I know the link force, I will probably use equation 6 to solve for NB, then use my friction equation to solve for the force of friction, plug it into equation 5, and solve for P. We sometimes in this chapter had problems where we had multiple things stuck together. And the thing I want to remind you of with that is just like when we were doing frames and machines, when you draw these free body diagrams, say a diagram of block A, B, and C, on those interfacing surfaces, you need pairs of equal and opposite forces. So if I draw the normal force at A, or the normal force that block B puts on block A as NAB upward, it would need to be downward on the other object. And I do the same thing here. If I drew a normal force BC here, I need a normal force BC that's opposite. Draw my final normal force at the bottom, normal force at the ground, if you want to call it that, just normal force at C. I would want to put my weights on here. So I'd have the weight of A, I'd have the weight of B, and I'd have the weight at C. I've also got an applied force P and a tension in that cable that I've removed. So I've got all the normal forces on for every surface that I've pulled apart. I've got all the externally applied forces that I know of. What I've got left to put on here are friction forces. And the way I like to start with friction forces is start with a block you know is going to move and the direction you know it's going to move in. So this block in the middle is going to move to the right because of a force P. Friction needs to oppose that motion. So the friction has got to act to oppose the motion. So there's the friction force on surface AB. Friction acts to the left on that surface. It's got to act to the right on the surface up above it. On the purple surface between B and C, again, the block wants to move to the right because of P. Friction has to oppose it. So you would draw friction that way. The force of friction on BC has to be in the opposite direction of the other interface. So these guys have got to be equal and opposite. And then finally, what about that bottom surface? Which way will that friction force act in? Looking at this diagram, I've got the only X force acting on it so far is the purple friction on top, which is tending to want to push the block to the right. So that means that the surface on the bottom has got to oppose that rightward tendency to move by going back to the left. Force of friction at C has got to act to the left. And if you look at every one of these diagrams, each one has got at least one force acting to the right and at least one force acting to the left so that it can be in equilibrium. Friction, it is very helpful if you get the direction right to begin with, which is why you really want to visualize which way will this move? It'll move right. So friction has to act left to oppose it. And then you use the direction of these 2 frictions on block B to figure out the direction of the frictions on the other blocks. And then finally on block C, because it's got this friction tending to pull the block to the right, the ground is going to resist that and tend to keep it, hold it in position. So in the case situations where you're not sure what's going to happen, Usually assume one particular kind of sliding, then go back and double check if the surfaces that you thought would not slip have enough friction to prevent them from slipping. All right, the one other kind of problem that we talked about with friction had to deal with tipping. And you might remember this example we did in class with two boxes, and this person is pushing right there toward the bottom of the top box. And we needed to try to figure out, will it tip? So a hint to know if you're going to have a tipping problem is you must know some dimensions. The trick to solving a tipping problem is you need to sum moments to find the location of the normal force, right? So if I just draw this, I'm just going to draw the boxes all together. If I've got a force right up here, P, and I'm given this height, H, I have weight of the top box, weight of the bottom box. There will be friction at the bottom. And the question is that we have to answer with the tipping problem is, where will the effective normal force need to be to prevent rotation of the boxes? So we know we're going to have a normal force somewhere, so we need to find this distance x. When we're not pushing on it at all, x is probably 0, and the normal force will be centered right underneath the weight. But once we start pushing on it, this force tends to cause a big moment about that point. And so the normal force, the effective normal force, shifts right to try to counter it with a counterclockwise moment, right? P causes a clockwise moment, N causes a counterclockwise moment. We typically want to sum moments right there. So call that point O if we want. And if we want to sum moments about point O, they have to equal 0. And what we find is P times H minus normal force times X has to equal 0. We solve for X. And based on how wide my tower of boxes are, if X is greater than the width divided by 2, then it tips. Because if the effective normal force has to act off the edge of the box, it can't, so the thing will tip over. Okay, second to last topic. This is section properties, and I'm just going to talk collectively about centroids and moment of inertia at the same time. The idea behind finding the centroid, we did this first using integration, and I will not be putting any integrals on the final exam. We're just going to do this with summation, because next semester, when you take mechanics of materials, you will be doing a lot of I-beams or T-beams. And for these, integrals are not helpful. Instead, you need to be able to find centroids without them. So to find the centroid, the x-coordinate of a centroid, you need to sum up the x-coordinates of the centroids of all of the individual parts times their area and divide it by the total area. For the y-coordinate of the centroid, you're summing up the y-coordinates of the centroids times the area divided by the sum of all of the different areas. So if the overall shape is symmetric, there's no math involved, your centroid will be right smack dab in the middle. But for this T shape, I do need to do some work. So let's consider, maybe for X bar, I don't need to do any work because this also looks symmetric. So my centroid, my X coordinate of my centroid will live right on the middle. But for the Y coordinate of the centroid, I have to do some work. So first step is to define a coordinate axis to use. And that's really important because you need to measure all of the little Y tildes. Those are the centroids of each little shape. They all need to be measured relative to the exact same line. So what I would want to do is for my top shape, the blue part of the T, I would want to measure the Y coordinate of the centroid. This would be Y tilde. How far down is it? And it should be half of whatever this height is. So if this height is H, Y tilde would be H over 2. And that would go into the top part of your equation right here as Y tilde, and then you multiply it by the area of that blue rectangle. Let's say this is a green rectangle next, and I need to find the centroid location of that green rectangle. I need to measure it all the way up to Y. So that means that this Y tilde for the green rectangle is probably going to be H. It's going to be the blue H of the blue rectangle plus, call it H2, I guess, plus half of H2. And that is what's going to go into the top of this equation. Then you multiply by the area, And then the bottom of the equation is just summing up the blue area plus the green area. When we're done, we should get a number that is somewhere in between the first y tilde and the second y tilde. It should end up somewhere in between here. So that's the idea behind centroids. The mistake that students make is kind of the only mistake that students make, other than just a calculator mess up, is getting this guy wrong. They forget to include the other height. That's centroids. Next, we have moment of inertia. And again, we're not going to do, we did these with integrals in the class, but we're not going to use integrals on the final. Instead, we're just doing composite shapes. So the idea behind moment of inertia is we're going to find the moment of inertia of each shape. We're basically summing up the moments of inertia of each shape. And this is a table lookup for a rectangle. Moment of inertia about the centroidal axis is 1/12 bh cubed. Y prime would be 1/12 hb cubed. Let me draw a rectangle. B is the base, h is the height. Here are your y prime and x prime axes. So I want to be really clear about notation here. Whenever you look up moment of inertia in a table, it gives it to you about the centroidal axes for the shape. So this equation will give me the moment of inertia for the individual rectangle about its centroidal axes. Problem is, to sum them up, we need the moment of inertia about some other x or y axis. So we're going to use this handy parallel axis theorem multiple times to find moments of inertia. The way parallel axis theorem works is if you know the moment of inertia of a shape about its centroid and you know its area, you simply take the centroidal moment of inertia, add to it the area of that shape times the distance squared. So as an example, if we look at our I-beam up here at the top, and I wanted to find the moment of inertia of this I-beam about, say, this x-axis right here. For this green rectangle, I would first use 1/12 bh cubed. That would give me the moment of inertia about its centroidal axis. Let me put some numbers on here and work this out. If this height is, let's say, 1 inch, and this width is 8 inches. Okay, the moment of inertia of the green rectangle about its centroidal axis is 1/12 8 inches times 1 inch cubed. The moment of inertia of that green rectangle about the x-axis all the way down here is going to be 1/12 8 inches times 1 inch cubed. So its centroidal moment of inertia plus its area, 8 inches times 1 inch, times a distance squared. I guess I need a distance. So let's say the distance from the top to here, say that's 6 inches. So if I want to find the moment of inertia of the green rectangle about this x-axis all the way down here, I need to use the distance from its centroid to this centroid right here, which will not be 6 inches. It'll be 6 inches minus a half, so 5.5 inches. So I would plug in here 5.5 inches and then square it. That's how I would get the moment of inertia about the x-axis down here of the green rectangle. Then repeat for this blue rectangle in the middle. And if we're lucky, this is a totally symmetric I-beam. It looks like it is. And this x-axis happens to be already at the centroid. So for the blue rectangle, Ix prime equals Ix equals 1/12 its base. And let's say it's 1 inch wide also. One inch, and then its height would be, well, let's see, I said that this is 6 inches from the middle to the top, so it'll be 6 inches from the middle to the bottom. Take away the 1 inch for the two eyes on the top and bottom, so it's 10 inches tall altogether, times 10 inches cubed. Okay, so I've found the moment of inertia of the green rectangle, first about its centroid, then about the overall centroid. There are two of them. We'll say this green one on the bottom is exactly the mirror image of that. It is also just the same size, so it have just the same moment of inertia about its centroid, and it's also 5.5 inches away. It's 5.5 inches below, but that distance gets squared. So it doesn't matter if it's below or above, it's going to end up being a squared distance. So it's the same thing. So if I want to find the total moment of inertia of this I-beam about its own centroid, I would need to add up 2 of these green ones plus 1 of the blue ones. And I'd have the moment of inertia about the centroid of that full I-beam. The common mistakes that I see with moments of inertia are, first of all, with centroids, not using a consistent reference line for Y bar or X bar. Next is forgetting the parallel axis theorem or using it incorrectly. So this is always the moment of inertia about the centroidal axis. You're always adding to it the area of that exact same shape and the distance between its centroid and the other axis, which could be anywhere you're interested in. And that distance has to be squared. When you're done, double check. Moment of inertia should always have units of length to the 4th. Area is length squared. When you take another length and square it, you get another length to the 4th. Also, your moment of inertia of any shape about its centroid should be the smallest. So when you add something to it, this should always come out to be bigger. And then finally, I see a lot of wrong distances in the parallel axis theorem. Always from the centroid of the shape of interest in the blue rectangle versus the green rectangle, or up here, this green rectangle or that blue rectangle. Find the shape you're interested in. Find the distance from its centroid to the axis you're interested in. In the case of the blue rectangle, the centroid of the blue rectangle matched up with the overall x-axis, and so my distance is 0, which is why I didn't need to use the parallel axis theorem, or you could say I used it and plugged in distance equals 0. Okay, finally, fluid statics, the only other topic that we haven't really covered in this review yet. So the idea behind fluid statics is simply that pressure depends on depth. In SI units, you'd say pressure is rho gz. And in English units, you'd say pressure is gamma times Z. Rho is density in kilograms, usually per cubic meter. Gamma is specific weight, which is in units of pounds per cubic foot, usually. Once you have pressure, what you want to do is convert that pressure into a distributed load. Distributed load W is pressure times B, where B is the length into the page, or breadth, if you want to think of it that way. So breadth is not actually visible on this diagram. 1 meter is kind of the width, 3 meters is the depth underneath the water. Breadth goes into the page, so it's going to say maybe this is 5 meters or 10 meters long, how long this dam is. So you need to multiply your pressure by that. Pressure has units of things like PSI, pounds per square foot, or newtons per square meter. You multiply with this, and then you get distributed load units. If I have, let's say it's just a plain old vertical wall under the water, once I have this as a distributed load, it's going to be a triangular distributed load or a trapezoidal distributed load. But if it's triangular, now I know W at the bottom right here. So I can now find the area under this curve and replace this with a single point load force from the water. And that force from the water is equal to the area under the W curve. And where is it going to be located? At the centroid of that W curve, which you guys might remember for a triangle is going to be 1/3 of D. We'll call D the depth if this is D. So this is the idea, just a couple of additional equations. I will be adding those to your equation sheet to make sure that they're on there for the final exam in case you get a problem like this. You need to find the pressure, figure out what units you have, and use one of these equations to find the pressure. Once you have the pressure at a particular depth, multiply by how far into the page that goes to get distributed load magnitude. Once you have distributed load magnitude, then you can find the area under this curve. For a triangle, it'd be 1/2. This base is W, times this height would be D. Well, what about a curved surface like this? My tip for a curved surface is don't do the curved surface problem. Break this up into instead a situation like this, where you've got your overall horizontal force comes from the force acting on a vertical slice of water. It's the same exact horizontal force that you'll have net acting on your curved surface, but it's much easier to calculate. So we do this exactly like the previous problem, and that will give you overall your horizontal force. And then for your vertical force, you need to find the weight of that water, because that's what's going to be the vertically downward force. If you can find that overall force and draw it at its centered location, that would be your vertical force. It's equal to the weight of the water above it. So let's work out the math here. We're given that this wall is, the seawall is 5 meters into the page. So that's our B. And we're given that the density of this water, seawater, I think, 1020 kilograms per cubic meter. So following the formula, this is an SI problem, so I'm going to use density times G times Z as the depth. So to find the pressure at the bottom, it's going to be rho W G times Z at the bottom, which is 1020 kilograms per cubic meter. G is 9.81 meters per second squared, and Z at the bottom is 3 meters. So we get the pressure at the bottom is 30.02 times 10 to the third newtons per square meter, or pascals. I like to convert that into distributed load. So the distributed load at the bottom is that times B. So that's 30.02 times 10 to the third newtons per square meter, and B is 5 meters. So this comes out to be 150.1 newtons, times 10 to the third newtons per meter. You could make that kilonewtons per meter. 150.1 kilonewtons per meter. So now how do we get the horizontal force? We're going to do the area under my red triangle. So the horizontal force is 1/2 the base, which is W at the bottom, 150.1 kilonewtons per meter, times the height is 3 meters. And that comes out to be 225.1 kilonewtons, and it acts 1 meter up from the bottom because it's 1/3 of 3 meters. To figure out the vertical one, I need the weight of the water. So here's where you go look up in the back of the book. And if you have a parabolic section, there's two kinds of parabolic sections, right? You've got the inside part of the parabola, whose area is 2/3 A times B. And then the outside part of the parabola is 1/3 A times B. That's in the back of the book. I will not give you any shapes on the exam that aren't already on your equation sheet. So to get the weight of the water, it's going to be the density of the water times G times volume of the water. That's the volume of the water inside this little parabolic area. I'll need to find that volume. It's going to be this area times the depth into the page, the 5 meters. So this should come out to be 1020 kilograms per cubic meter times 9.81 meters per second squared. And then volume is going to be 1/3 AB. So that's 1 meter. A and B are this 1 meter and this 3 meters. 1 meter times 3 meters, that's the area. And then the depth into the page is 5 meters. And if you multiply that all out, you get 50 kilonewtons. And if you needed to know exactly where that acted, go back to the table in the back of the book and look up the formula for the centroid of this area that's outside of the parabola. If you need the resultant force, well, we just got the horizontal component. We've got the vertical component. So you can use Pythagorean theorem to combine horizontal and vertical by squaring them, summing them, and taking the square root. And if you do that, you get the total resultant force. It's the square root of 225 kilonewtons squared plus 50 kilonewtons squared. That comes out to be 231 kilonewtons. This completes your final exam review for statics.